Good morning to everyone. My name is Dr. K. Lalita Ambike, working as Assistant Professor, Department of Physics, KUSR College of Engineering, Tiruchendur. Today, we are going to discuss about the basics of magnetic materials. This slide introduces the concept of magnetic materials using two powerful visual examples. Consider top image. So first image, this is a classical demonstration of a bar magnet surrounded by a iron fillings. So the fillings align themselves along the magnetic field lines, visually representing the invisible magnetic field. So you can see how the lines emerge from the north pole. It indicates the N and curve around to enter the south pole. It indicates S. This shows how the magnetic forces act in space around a magnetic object. If we consider the second image, this image represents the Earth's magnetic field and how it interacts with solar wind from the sun. The sun emits charged particles which are deflected by the Earth's magnetosphere. The Earth's magnetic field protects the planet from harmful solar radiation and plays a crucial role in navigation and atmospheric shielding. So, together, these images emphasize that magnetic materials generate fields that can influence their surroundings. So the magnetism is not just a lab phenomena. It plays a critical role in planetary and cosmic scales as well. Illustrates how magnetic materials are widely used in our daily lives and technology. These applications rely on different magnetic efforts such as attraction, induction, storage, or motion. It creates high impact in technological applications. So definitely hair dryer. So it contains a small electric motor and often a heating element. So magnets helps run the motor. So then microphone uses electromagnetic induction to convert sound waves into electrical signals. Then hard disk. So it stores data magnetically on rotating platters. So essential for computer memory systems. Then speakers. So it converts electrical signals into sound using magnetic coils. So then keycode. So it uses a magnetic strips to store and read security data for access control. So then definitely MRI scanners. So uses powerful superconducting magnets to generate magnetic fields that help image the inside of the human body using nuclear magnetic resonance. So also we can see common daily uses. See electric motors. So it has small DC motors in fans, toys and devices use magnets to create rotational motions. Then door locks. Definitely the door locks. So the electromagnetic locks are used to secure access control systems. Then we know about the bats. So magnetic buttons, snaps used to for easy closure. Then we know about the compass. A classic tool using a magnetic needle to align with a X magnetic field. Then pencil boxes. So the children uses the pencil boxes. So the magnetic plate is used to closer. Fridge magnets. So the stickers and decorations held by magnets on metallic surfaces. So definitely you have used mobile phones and mobile covers. So the phone covers often include magnets to attach or trigger small functions. Then pin holders use magnets to keep metallic items like paper clips in place. Then magnetic crane, heavy duty industrial crane uses electromagnets to lift and move scrap material. So the magnetic materials are not just for a science labs, they are integral to medical technology, transportation, data storage and household convenience. So this highlights the versatility and importance of magnetism in modern life. Magnetism. So the magnetism arises from moving electric charges. It explains that there are two types of magnets. So one is permanent magnets, another one is electromagnets. So the permanent magnets which retain magnetism. and electromagnets which require electric current. The magnetic field is generated due to the movement of these charges. This slide explains that an electron has spin, and due to this spin, it behaves like a tiny magnet with a north and south pole. It means a dipole. So the direction of the spin determines the orientation of the dipole. This magnetic dipole moment is a key contributor to the creation of magnetic fields at the atomic level. Small particles like electrons and protons have properties like mass, charge, and the intrinsic magnetic moment. So the magnetic moment describes how much like a magnet these particles will behave. So the electrons and protons both have magnetic moments, but the electron's moment is approximately 1000 times is stronger. If an electron cell has paired electrons, their magnetic moments cancel out. If a cell has unpaired electrons, the atom shows magnetic properties. So the atomic orbital models showing paired versus unpaired electrons. Additionally, magnetic moment vectors cancelling or adding. This slide explains the origin of magnetism at the atomic level, focusing on two types of magnetic moments. First, we see orbital magnetic moment. So, electrons move around the nucleus in orbitals, similar to how planets orbit the sun. So, this revolutionary motion of the electron creates a tiny current loop which generates a magnetic field. This is referred to as the orbital magnetic moment. So then another one, spin magnetic moment. So electrons also spin around their own axis. So it is indicated by the red circular arrow. So this spin motion produces an additional magnetic field called the spin magnetic moment. So the direction of the spin determines the direction of this magnetic field. So the magnetic behavior of the materials in atoms where electrons are paired, their spin magnetic moments cancel each other out. But in atoms with unpaired electrons, the magnetic moments do not cancel. These unpaired electrons contribute to the net magnetic moment of the atom and are responsible for the material's magnetic properties. So finally, we concluded the magnetic property of a material depends heavily on the number of unpaired electrons in its atoms. So the more unpaired spins, the stronger the magnetic behavior will be happen. Okay, let's now look at how an individual atom behaves like a tiny magnet. On the left, we see a simplified model of an atom acting as a magnet with a north N and south S pole. So the arrow indicates the direction of the atom's total magnetic moment. So this is the combined magnetic strength and orientation of the atom. So now let's look at what contributes to this magnet moment. So on the right side, we break it down into two components. So first we have the orbital magnetic moment. So this comes from the electron revolving around the nucleus. So just like how the current loop creates a magnetic field. So second, we have the spin magnetic moment. So this comes from the electron spinning around its own axis. So like a spinning top. So it also produces a magnetic field. In some cases, these two magnetic moments, it means orbital and spin. So add together shown in the insert below. So enhancing the atom's total magnetic strength. But in other atoms, depending on the direction of the spin, they might partially cancel or reduce the total moment. So the total magnetic moment of an atom is the vector sum of its spin and orbital contributions. So this concept is key to understanding why certain materials iron or cobalt, so are strongly magnetic materials while others are not. It's all about how these tiny atomic magnets align and add up. Okay, now let's explore the concept of magnetic dipole and its dipole moment. So which are key to understanding magnetic materials at a deeper level. So a magnetic dipole consists of a pair of equal and opposite magnetic poles. So like the north and south poles of magnet. So that are separated by a small or finite distance. So you can think of it like a tiny ball magnet. So dipole moment is a measure of the strength of this magnet. As shown on this slide, the magnitude of the dipole moment is calculated using this formula. So capital M vector is equal to small m into 2L into I cap. So each letter represents M is the pole strength, 2L is the distance between the poles, so L is half the separation, and cap indicates the direction along the axis of the dipole. So these values tells us how the strong mag is and in which the direction it acts. So the SI unit of the pole strength is ampere meter, and since the moment is a product of this with distance, and the unit of dipole moment is also ampere meter square. So importantly, the direction of the dipole moment is from the south pole to north pole, which is opposite to direction of the magnetic field lines that go from north to south in space. So this concept applies not only to physical magnets but also to atomic and subatomic systems where magnetic dipoles arises due to moving charges. Okay, this slide gives us a comprehensive view of how magnetic poles behave, how the magnetic field lines are formed, and how magnets interact with each other. So first consider the top left. Here we see a Bohr magnet with clear magnetic field lines emerging from the north pole and curving around to enter the south pole. So next consider the center right. This is a great illustration of how magnetic field lines behave between two magnets. In the top diagram, opposite poles, it means N and S, are placed near each other and the lines flow smooth from one magnet to other. So this shows attractions. In the bottom diagram, similar poles like north to north or south to south face each other and you can see the lines pushing away. This is the repulsion. So then bottom left, another example of a magnetic field around a Bohr magnet. So with a compass needle aligning tangentially along the field lines. So this shows how magnetic compasses work by aligning themselves with the Earth's magnetic field. So now consider the right column. The top image says it all opposite poles attract. N is pulled towards S and vice versa. So the bottom image shows that the same poles repel. It means north to north or south to south. So then push each other away. So finally, we concluded the magnetic fields are invisible but have very real effects. So understanding the behavior of poles and field lines helps us explain how magnets attract, repel and interact with each other. So whether in simple toys or in advanced technologies like magnetic levitation trains and MRI machines. In next video, we will meet again. One of the another interesting topic is types of magnetic materials. Thank you.